How did you accomplish that?
Yes. Okay, right. So what was I saying? I was apart from cursing the computer, I was saying that I think this is a good thing to talk about at this meeting, because not only is it a very famous experiment, but it's also, a lot of the background to the experiment is contemporary with the developments we're celebrating here with Slipher's measurement of the spectrum. And the establishment of the interpretation of the apparent redshifts of galaxies, of course, depended on the establishment of general relativity as the preferred theory of gravity. And this experiment was crucial in giving credibility to Einstein, experimental credibility to Einstein's theory. So the other reason is, of course, that I wrote a book about this experiment a few years ago, and I thought it would be a good opportunity for a sort of crass bit of commercialism. So if anyone's hostile to that, all I'll say is, buy my book. So the story starts, of course, with Newton. We've had some comments this morning about various historical aspects to this, including a not very complimentary comment or two about Newton's philosophical or theological motivations. Of course, the difference in Einstein's theory to the prevailing Newtonian view of mechanics is that Einstein's theory dispensed with the idea of absolute space and absolute time. Space and time became part of the play, not just the stage. And you can see that put rather dramatically here in this excerpt, which is from the general scholium of the Principia, which I've taken the liberty of translating using my schoolboy Latin into English. So it's not just an assumption, there's actually a very deep religious motivation for Newton's preference of absolute space and time. The supreme God is a being eternal, infinite, and absolutely perfect. He endures forever and is everywhere present, and by existing always and everywhere, he constitutes duration and space. So Newton's actually saying there that absolute space and time are a manifestation of a God. He was a Unitarian, he was a rather heretical version of Christianity, but that was very strongly present in his motivation for the theory. That all changed with Einstein, of course. I always like that picture because he looks really clever in that picture. Of course, we know he's really clever. He might well have just been writing out a shopping list or something. So clever when I say things. The theory of general relativity, of course, was published in 1915. There's actually a very large number of quite small papers came out immediately after that, analysing various observable situations in the context of the theory. Now, I'm not going to go in. One of the things that I like about this experiment is that it's quite easy to explain, at least in a phenomenological sense, what you'd see in this experiment without using the full panoply of general relativity or the mathematics. So it's quite a good thing to explain concepts of general relativity to beginning students, for example, because you can understand roughly what the experiment is about by just a few thought experiments, which Einstein was actually pretty good at doing. So let's have a try this. So here's the no maths version for why you get bending of light by the sun. So the theory of general relativity basically incorporates a thing called the equivalence principle, which is the idea that in some sense acceleration is equivalent to the existence of gravity in a mathematical sense of gravity. So here you can illustrate this with the pictures on the left here. This is a pointer. I look at technology here.
Show me your finger.
Yeah, I have a digital but also a manual pointer. So here's just a very quick cartoon view of this. So this is a laboratory, or actually a lift, with a sophisticated piece of physical measurement apparatus in it, a spring with a weight on the end. And the idea is that this lift is static in the Earth's gravitational field, locally in the frame. So what happens is that the Earth's gravity pulls the weight down and stretches the spring. Now the equivalence principle more or less says, suppose you take the lift and you put it in intergalactic space a long way from any gravitational field, but accelerate it in this direction with a rocket. Your intuition suggests that the spring will kick back if you accelerate like that. And the equivalence principle basically tells you those two things. Inside the lift, you can't do an experiment which would distinguish between those two situations, whether you're static in a gravitational field or accelerated. The other way of thinking about this is if you take the lift and put it in empty space and don't accelerate it, the weight will just float freely there, so you will not measure any forces on the spring. And the same thing will happen if you're in a gravitational field, but accelerating in free fall in response to that gravitational field. The weight will appear to be weightless then. So there's an exact cancellation between gravity and acceleration in response to it. So that's the equivalence principle. And why does that mean that light should bend in the presence of a gravitational field? Well, if you take your lift and you move a lift, there's another piece of apparatus in the lift here. There's a laser, which is shining from one side to the other. If the lift were moving at a constant speed, the laser light would hit the wall exactly opposite from where it set out. If, however, the lift accelerated, in the frame of the lift, the light ray would seem to be bending. Okay? So this is special relativity where the lift is moving at a constant speed. In general relativity, you sort of think about it being accelerated here. And by the equivalence principle, if you put the lift in a static situation in a gravitational field, the light ray must do the same thing. Bend. So the gravitational field bends light. And the picture we always get is that when you have no gravitational field, light travels in a straight line. This is what happens in a Newtonian picture as well. If there's a gravitating body like a star, sun, a black hole even, then the light actually still travels the shortest distance in the corresponding space, but because the space is now curved by the action of general relativity, it's not a straight line anymore. It's a geodesic, but it's not a straight line. In fact, the effect we're looking for in the Eddington measurement is much smaller than this diagram suggests. But in a much stronger gravitational field, the angle that the light ray can be deflected by can be 360 degrees. You can get photons going in orbit around the black hole. Okay, so that's just the cartoons. This is what you actually see during the eclipse measurement. This is not to scale, except perhaps in the physicist's mind. Depends on the physicist, of course. So the idea is that you basically look out at a field of stars, and those positions can be measured quite accurately. I'm going to that in a moment. But if you then suddenly put a huge gravitating body in front of those stars, the light rays from the stars would be deflected slightly. And the curious result of that is that what you measure at the Earth is the direction that the light ray comes into the telescope or the eye of the observer. So you trace back along this, and rather than seeing where the starlight actually came from, you see where you think it came from, which is further out. It's deflected outwards. So the idea is you measure the positions of the stars, you then wait. Of course, the problem is the sun is quite bright. Right? So you need a convenient thing to block out the light of the sun so you can measure the star positions in the background, and that is an eclipse. So if you have a total eclipse of the sun, you don't see the sun anymore, but you see the stars in the field, and you measure them, you'll find them further away from the sun's limb than they were when the sun is not there. Okay. Now the angular deflection you can calculate, it's 4gm over rc squared for a line of height which just touches the sun. This is the radius of the sun here. And that's very, very small. Even very close to the sun, the deflection is 1 3/4 arc seconds. The sun is actually big, but it's not a great, it doesn't produce a strong gravitational field. So I just thought I'd give you the history to this. There is a Newtonian prediction of light bending by the sun, but you can't find it in anything that Newton actually wrote. He may have done the calculation that everyone refers to as the Newtonian calculation, but it may well have been among the papers that were destroyed when his little dog knocked the candle over. In the Optics, however, very interesting book written in English, not in Latin like the Principia, it is punctuated by a series of rhetorical questions. And one of the rhetorical questions Newton asks in the Optics is, do not bodies act upon light at a distance and by their action bend its rays? So Newton clearly had in mind that gravity might do something with light, but there's no calculation. The first calculation of what would happen to light in a Newtonian gravitational constant was Soldner, and he got a value, alpha here is the number I referred to on the previous slide, less than a second of arc for grazing incidents, and that became known as the Newtonian prediction. Now that was all done long before Einstein. In 1907, so in between 1905 when he had special relativity and 1915 when he got the full GR theory, he thought about how he might calculate this effect. And he got the Newtonian answer. But it was quite interesting because he didn't know anything about astronomy, and he thought a second of arc or less was basically far too small to be measured by anyone human. It's about the width of a human hair at 30 feet or something. It's a tiny deflection. So he basically didn't do anything with this result. In between 1907 and 1911, he visited some astronomers in Poland, and they said, actually, that 1 arc second is no problem, we can measure that without any difficulty at all. So he then published a prediction of the light bending by the sun. Essentially, what he did was he used Newtonian gravity, but replaced the mass of a light particle by using E equals mc squared, putting the mass from there. So you got the Soldner answer again.
Question: was he aware of Soldner? Einstein?
I believe so, yes. Yes, he was. But he was doing it in a slightly different way. Yeah. In fact, it's anyone's guess really what the Newtonian prediction should be, because light doesn't have mass in Newton's gravity, right? So you might argue that it doesn't feel gravitational field at all.
In relativity, it has mass.
Yeah. Yes, it does. Yeah, that's right. But if you're purely Newtonian, if you haven't heard anything about relativity, you might well just say that this Gmm over r squared you don't get. There's no mass, so you don't get.
You've got another 10 minutes.
Okay, I'll accelerate slightly.
So, the famous gravity.
Take some of that out of my time.
So with the full theory of general relativity in 1915, he did the calculation properly and found that the predicted deflection is actually a factor of 2 larger. That's just an old slide. I put that in response to some comments this morning. This is the accuracy of astronomical position measurement as a function of time. And you'll see that around about 1900, this is from an old book from about 1925. I should, in the light of this morning's discussion, perhaps have obliterated Van Harman from here, but you can see that by 1900, the accuracy's 3/100ths of an arc second. So that's actually well within the capability of measuring a deflection this big. The factor of 2, if you want to know, comes from the fact that if you just use E equals mc squared, that's tantamount to just using the time part of the metric that this is the Schwarzschild metric, which describes the gravitational field around the sun. If you have the full theory of general relativity, you also know about curved space, not just the effect on time and acceleration. So there's another term that has to be taken into account, and if these things are small, you'll see that it's an additional effect in the same direction as the first one. So that's where the factor of 2 comes from. Okay, meanwhile, back in England, people were already, before the general relativity predictions were out, were thinking about measuring light bending by the sun. In fact, Eddington, the subject of this talk, had already been on an eclipse expedition himself to Argentina, but it was clouded out, rain stopped play, and they didn't get any measurements. Interesting to speculate. Remember, Einstein had published a paper with the Newtonian prediction on it. Had they measured something then, one wonders what the consequences for Einstein would have been, because they were delayed. Now, if another figure we've heard about this morning was de Sitter, Eddington actually got the papers. There was a war going on, of course, in 1915-16, when general relativity was produced, the theory was produced. And Eddington got the paper via de Sitter, who was in Holland, which was neutral during World War I. And they started discussing this, and then in 1917, the astronomer Royal Dyson realized that the eclipse coming up in May 1919 was actually perfect for doing this. 5 minutes. Okay, here's some pictures. I'll just tell you a bit about the eclipse. So this is the date. There are two reasons why it was really good. One is that the maximum length of totality for a total eclipse of the sun is about 9 minutes. The duration of this eclipse here would have been about 7.5 minutes, so that's actually very good if you need to make a lot of repeated measurements. The path of totality, here we are, took it across the Atlantic here, and so it was decided to send expeditions to both Sobral in Brazil and Principe off the coast of what was then called Spanish Guinea. This is a picture made by one of my undergraduate students. I have a project each year where the students reanalyze all of this data, because it's quite important data, just to see what the conclusions are. This is where the sun is in the field for the two positions in Sobral and Principe, and these are the star positions. You'll see it's actually very fortunate because the Hyades cluster is right behind the sun during totality in this eclipse. So you got a number of very bright star positions to measure. This is a very fortuitous situation for an eclipse. It's no use at all if you only have 1 or 2 stars. Okay, historical background. Eddington, remember there's World War I's going on. Eddington was a Quaker and a pacifist and a conscientious objector. He would have been, but in fact there was no conscription in the British Army until 1917. This was largely to replace disastrous losses on the Somme offensive the year before. Eddington made no secret of the fact that he would not be drafted. Many of his Quaker friends had already been imprisoned as conscientious objectors, and he expected the same thing to happen to him. He didn't see why he should be treated any differently. Dyson, the astronomer royal, basically brokered a deal with the bigwigs to get Eddington off doing this and send him on an expedition to measure the bending of light by the sun. Eddington almost blew the deal, actually, by being very stroppy in an interview with the Home Office officials. But in the end, that deal was brokered. Some interesting facts. Huge grant given for this experiment, £100 for equipment, and a huge amount for travel, because they had to go by boat there and back to the 2 locations. They stripped 2 astrographic object lenses, one to go to Principe and one to go to Sobral. These were basically taken out of astrometric telescopes at Oxford and Greenwich, respectively. So Sobral, they also took a small 4-inch telescope as a backup, and all the good data came from this. If you analyse it. I'll skip forward because I'm running out of time.
About 2 minutes.
Yeah. So here's this is from the London Evening News of 1919. It's quite a nice picture. It's a picture of the experimental setup. The dotted lines, of course, are there to guide the eye. That doesn't actually happen during an eclipse. The telescope, you see, is mounted horizontally, and it's got a sort of mirror effect, or the coelostat there, which is driven to keep the stars in the field of view. So Eddington went to Principe because he was told the weather would be better there than it would be in Brazil, and he wanted to have all the good results. Andrew Crommelin, went to Sobral. Eddington had endured a tropical downpour the morning before the eclipse and was nearly drowned, never mind washed out in terms of the experiment. Cromlin had good weather, and the upshot that you probably all know is that the results were presented as supporting Einstein. There are 3 telescopes, remember. Well, here's just one of the plates. 2 stars in there, which you can hardly see. The corona's very big during the 1919 eclipse. Probably can't see the 2 star positions here. The paper is this. I looked up this morning, actually. Those of you who are cynical about citation statistics, here's a good one. Probably the most important astronomical measurement of the 20th century, I would say, possibly. Published in 1920, 81 citations altogether since then. That's less than 1 a year for 19.
They don't make citations very interesting.
So the thing is, I'm not going to be able to go into the data. Data analysis, this is a hard experiment to do, and I'll just explain why. You might think that you just take a measurement of the field without the sun in it, and then the eclipse field, and you compare the 2 and you read off the gravitational deflection. In fact, the measured deflections between these 2 situations are the gravitational deflection is only a part of what could go wrong. There are other errors. You might get the 2 plates slightly off-centered. You might get a scale slightly different in the 2 plates. You might have one plate rotated to the other. So you need to solve for the astrometric part of this thing before you can actually isolate the part that's due to gravity. So you need a lot of measurements of star positions in order to get these additional parameters and take them out of the problem.
3 more.
Sorry?
3 more.
Well, we
No.
have to continue if you want to finish, because in 3 minutes we have, with no discussion, we have to go to the next speaker.
Okay, so what I'll say is that you actually need more than, you need as many as you can, because you have to remember that these have got errors on them too. This is not a straight determination of, it's not a question of solving simultaneous equations. These are all uncertain, so you actually have to put them all into a least squares type thing, solve that and minimize the error. So the more you get, the better, but you need at least 4. At least 4, actually there are something like 11 that were used. I'll just skip to the bottom line. You see that the Principe astrographic, the one that Eddington himself measured, gave alpha of 1.62 plus or minus 0.45. Remember, alpha is 1.75 or something for the Newtonian, for the Einstein value. Now, in fact, that analysis, because these eclipse plates were taken through cloud, there were only 2 measurable star positions on each plate. So he couldn't actually get a proper astrometric solution for this, and he basically made it up as he went along in that sense. The Sobral astrographic had problems with the optics, and they got bang on the Newtonian value. The small Sobral telescope gives beautiful measurements and gives a high value consistent with Einstein. Now, the controversy about this is largely because Eddington included the results of the Principe plates, where basically you could, if it had been me, I probably would have just thrown them away, but that would have made it a 1-all draw, basically, and he had to include this in order to get a 2-1 win for Einstein. So you can argue a lot about the quality of the analysis of it. A footnote to this, which is interesting, was that the Sobral astrographic plates, these are the main plates, were actually remeasured in the 1970s by a team from the Royal Greenwich Observatory. And they got results completely consistent with the small Sobral astrographic. So it seems there was something wrong with the measurement of the plates as well as the optics of the telescope. I still don't know what that is. These plates still exist somewhere, and I would love to remeasure them. But
Not according to the Royal Astronomical Society.
the Eddington plates are lost, the Principe ones, but the Sobral plates are in a large and uncatalogued plate archive that used to be owned by the ESA. So anyway, here's a plot of the deflection that you can see there for the important stars in the Sobral plate. This is the Einstein prediction, and this is the Newtonian prediction. So I think that's reasonably convincing from the Sobral data. Just to show you how hard it is, here is a star image from one of the Sobral plates. 5 arc-second seeing during an eclipse. And that's the measured deflection at that star's position that you would expect for the Einstein value. That's the large deflection. So you can see what the problem is. You have to get the centroid of this mush very accurately in order to tell that it's been deflected by it. You can do that sort of thing, but it's not easy. So I think I'm going to skip that. I'll just say one or two other things. One interesting fact. People think that 1905, the special relativity, the photoelectric effect, and so on, was what made Einstein famous. In fact, it wasn't. It was this. If you look in the New York Times annual index of proper names, you find no mention of Einstein in it until 1919 at all. And then after 1919, there's not a single year without a mention of Albert Einstein. So there was a phase transition in 1919. Why? It was a scientifically important result. It was a little bit controversial, but it was also very important sociological and historical things going on. It was the end of the First World War. German theory, British experiment, it was a kind of reconciliation. There was also a sense of overthrowing the old order, the Newtonian order. I think people wanted to have, the old hierarchy of pre-war politics had taken Europe into a terrible conflict, and people basically wanted a bit of a change. I think that filtered through. These are just some of the other headlines from the Times of the day that revolution in science, new theory of the heavens of the universe was put in. This is the report of the Einstein prediction. So there's a lot of things going on in the aftermath of the First World War. The other thing I'd like to say, just quickly, is that there were two expeditions, one that Eddington himself went on in 1912, and another in 1914, which was a German expedition, actually funded by Krupp's, went to the Crimea to try and measure the light deflection. But unfortunately, the war started, and the team, basically half of them came back to Germany, and the other half were interned in Russia. So that they never got anywhere. But it's interesting to speculate what would have happened if these measurements had been made while Einstein's name was on the wrong prediction, as it turned out. It's worth saying that it's actually, despite the controversy of the analysis, better experiments were done over the next 20 or 30 years. It's always difficult to do this kind of measurement with optical observations during an eclipse. But if you use radio observations, you don't need an eclipse, because you can do them in daylight. And the accuracy of positional deflection measurement using radio observations is milliarcseconds, not a tenth of an arcsecond or worse. And they confirm the Einstein value very accurately. And now, of course, we have a whole industry of using gravitational lensing on large scales. I just put this picture in because it's a beautiful one from a long time ago. We now use something which used to be a test of general relativity as a tool to make astronomical telescopes even larger, using lensing to see distant objects behind them. So, sorry about the kerfuffle at the start, but that finished now.
I thought I'd like to go through the discussion time as well. Didn't want to cut.
That's fine.
So thank you again. Well, we have to be fair to the next speaker.
Can I make one correction? The plates have been re-examined carefully over 20 years ago by an astronomer called Patrick Wayman, and he found exactly what you showed there. He redid it from scratch. And the reason that, the result, it's not a one-off draw, because if you look at the figures you showed, the experimental error on one of those is much larger than the other. And he published that 20 years ago. Everybody forgets all about it.
No, I did say that the Sobral measurements were redone, and they're in line with. Okay. I was just quoting on that slide the numbers that are in the Eddington paper from 1920.
But it's not a one-all draw. Does it mean even within the Sobral plates? Because the error of one is
sure.
They're consistent with anything. They are so big.
Yeah.